in the previous section, we discussed numerical and graphical summary when one of the variables is categorical, and then the other could be either categorical or it could be quantitative. So of course, this begs the question, what about having two quantitative variables? How do you describe them with numbers, and how do you describe them with graphs? So that's what we're going to be doing now. So we're going to be talking at Scatterplots. So that's going to be the graphical summary and correlation. So here are the learning outcomes for you, which you should be looking at when you do your revision. So you should be able to produce and interpret a scatter plot at the end. You should be able to describe the nature of the relationship between two quantitative variables, and we'll explain that later. You should understand how the formula for the Pearson coefficient of correlation works, how it was obtained, and what it means. And also know, what indication it gives you exactly. Sometimes it works and sometimes it's a bad idea to use it. And you need to know what's the appropriate graphical and numerical summary to study the relationship between two quantitative variables. So we're going to start by, we want a useful graph for two variables which are both quantitative. And the answer is right there, ta-ta. You need to use a scatter plot. So we will be using, when both our variables are quantitative and we want a graphical summary, we'll use a scatter plot. I'm sure you've seen those. That's when you have an x-axis and a y-axis and you have one variable on each. And the reason why this is the right tool is if your variables are quantitative, then it makes sense to put them on an axis. The difference between two values has a meaning, they're on a scale. And this is where your axis comes from. Here is your first example of a scatter plot. So each dot here corresponds to one family. So for example, if I look at this family, the temperature inside their house is something like maybe 12 degrees, and the amount of electricity they're using is close to maybe 55. So each dot corresponds to one family or household, but I find this much harder to pronounce, so I'll stick to family. So that's what we mean here. The two variables must be measured on the same cases. One case, one family. And you notice that there is a shape a little bit like that, so it's not really linear. Now you will need to be able to produce some scatter plots, and what you could just do, you just search in the slides and come back to that, and then you reuse this. So first, you need to go get the information. So you have a file called electricity usage, lusage.txt, and you need to import it into R using read table, and you put that in an object called electricity usage, basically. It has two columns, one column called temp for temperature, and one column called usage. This $sign just is a way of extracting the column of interest. So in X, you will have a list of numbers, and the first one will be the temperature in the first house. The second one will be the temperature in the second house, and so on. So for Y, you want to use this same data set, and you want to extract usage. So that's your second column. And so that's really a list of numbers, and the first one is the usage in the first family, the second one, the usage in the second family, and so on. Your goal was to produce a scatter plot, so you need to plot. On the x-axis, you called it x because you were going to put it on the x-axis, then y, so x and y. Now you want to put a label on the x-axis, a label on the y-axis, and a main title. And this is the description of the dots. If you put nothing, you'll have the default and you will get a perfectly good scatter plot. In case you forgot, so this is why one of the instructions was to make them blue, as you can see. So once you have the scatter plot, you want to describe it. You want to describe the nature of the relationship. So there are four things you have to think about. And the first one is there a relationship? Because if there's no relationship, then there's nothing to describe. So if the relationship is non-existent, there's no relationship, just stop. Now, if it is existent, it could be strong or weak. It could be increasing or decreasing. When one variable increases, the other one tends to increase too. We will say that the relationship, is increasing. And if it increases on something that looks like a straight line, we will say that the relationship is linear. Whereas if you see some parabola or some other funny shapes or nothing, you will say that it's non-linear. And it's really the goal of producing the scatter plot, to describe it. So we're going to be looking at a few examples because you need to practice those skills about how to describe things. So I'm going to show you 4 scatter plots, and you will have to use the correct words to describe them. So let's look at this first one. It's really important that you do it rather than just listen to me. So remember, the first thing you need to do is to decide if there is a relationship or there is none. If there is none, you're done. If you think there is one, you need to decide, is it strong or weak? Write this down. Write what you think. Is it increasing or decreasing? So maybe you can take notes and put an arrow going up or an arrow going down. And the last thing you need to decide is it linear or not? Pause the video. So let's look. Is there a relationship? Yes, definitely. It's quite strong because you can see that the points are reasonably close to the curve, right? They're not spread all over the place. Is it increasing or decreasing? Well, as temperature increases, then the electricity usage goes down. So probably this is driven up by the heating in the house. See, if the temperature is 20 to 25, then you don't need as much electricity. And the last one is it linear? And no, there's this slightly curved pattern. Let's try another one. So now we see that we applied the log function to the electricity usage. Again, pause the video and try to remember what you need to write. So first, is there a relationship? Yes. Strong or weak? Fairly close to some line. Strong. Decreasing. And now it's linear. Actually, that's the reason why we applied the log function. For those wondering, it's the natural log in that case, but in R we write the log function. It's not unusual to use that function to have a linear relationship when initially you have a slightly curved pattern. Now this one, the question is, you make more money when you get older, basically. So here you have the age, and here you have the income. And every dot corresponds to one person. So that's their age and that's their income. Again, these scatter plots only work if one dot is one case. So the 2 numbers you get correspond to the same individual, same case. Again, try to remember how we describe, what we need to talk about. Pause the video, write it down. So is there a relationship? I would say there is, but initially, it's quite easy to describe, and then it seems to get much wider. So I would say that is there a relationship? Yes. So it would be existent, but it's quite weak because when you get to like 45 years of age, the points are pretty spread. Is it increasing or decreasing? Well, in that case, neither, right? It's decreasing around this age. If we got rid of that, we could definitely say that it's decreasing. So in that case, we can't really describe with one word. Maybe we could say from 20 to 30 years of age, the relationship is increasing, and after that, it's decreasing. And the last one is it linear? Obviously, no. Our last example is a scatter plot of UNSW satisfaction versus travel time. So when you say versus, the one after versus is the one on the x-axis. And we see that something strange happened here. A student answered 1,000 minutes as their travel time to UNSW. So maybe it was a typo if we're trying to enter 10 or 100, or maybe it was just a joke. But the thing is, because of that dot, this is very hard to see. And in that case, it can only be a mistake. That's 16 to 17 hours. I don't think that anyone spent that kind of time coming to UNSW every day. Let's see how we remove this. So once you remove the outlier, this is what you see. So basically, it's the same. It's the part you had initially, but the axis, it's been spread. And when you look at that, it's hard to think of any good pattern in that. It's more or less the satisfaction with UNSW is more or less flat and doesn't seem to depend on travel time. So in that case, we're going to say that there's no relationship or the relationship is non-existent, and that stops the story. We don't have to look at any of the others. It doesn't exist and it's weak. It's a bit strange. So So there will be cases where you know for sure the outlier is a mistake and you will want to remove it. So you will need the R code to do that. So again, I'll put this here so you can actually do search, remove outlier, Control F, and then you get that. It's going to take you here. So same beginning as before. So in the variable X, we've put the travel times. In the variable Y, the corresponding UNSW satisfaction. And now look here. We take X. We take off the numbers for which X is greater than 500. And of course, for Y, you need to remove the exact same one because each dot corresponds to one case. So if the X value is wrong, you want to remove the corresponding Y value, which corresponds to the same person. And now it's the same thing, except now you're plotting X1 and Y1, which are the data in which you have removed the strange answer. And you get the one we had earlier. So if you want to see it in writing, this is the conclusion we had. In the previous example, there was this outlier of 1,000 minutes to get to UNSW, and that seemed to be either a silly mistake or a joke. And so outliers like that will need to be corrected. But sometimes outlier can reveal things you didn't expect there. Let's see an example. So this is the 2000 US presidential election. So on the plot below, you can see the votes by county. So each dot is actually one county for the Reform Party candidate. So in 1996, the candidate was called Parrott for that party. And in 2000, it was called Buchanan. And you can see that for every county in Florida, there is a pattern, except for Palm Beach, which really stands out. It looked like suddenly in 2000, many more people voted for Buchanan than expected. So this raised a question. I mean, you see this graph and see what happened in Palm Beach. It turns out that in the US, every county has their own ballot on which you vote. And this is the one from Palm Beach. What you can see is, so the Democratic candidate who expected to get more votes was Al Gore. So Al Gore is second in that column, but to vote for him, you actually need to punch the third hole, whereas Buchanan, the Reform candidate, here corresponds to the second hole. So what we suspect is that a lot of people who actually wanted to vote for Al Gore because he was second punched the second hole, and they ended up voting by accident for Pat Buchanan, right? Punching the second hole casts a vote for the Reform Party. And very interestingly, if you remember this election, the votes in Florida were really close for Democrats and Republicans. And in the end, in that election, George Bush Jr. won by a tiny margin of 537 votes. And the way things work is in Florida, whoever wins Florida, whether they win by 51% or by 80%, they get all the votes from Florida, the 25 votes. And that's how George Bush Jr. became president of the United States, because of this difference of 537 votes. And if you look here where Palm Beach was supposed to be, and the number of votes they got, about 3,000, just Palm Beach would be enough to explain what happened. It's completely crazy, I think, and very clear on the drawing. So let's see where we stand. We just looked at Scatterplots, which are the tool to use if you want a graph for two variables when both of them are quantitative. So that begs the question. So each time we do numerical summary and graphical summary, now we want a number, which would summarize the relationship between two quantitative variables. So this number, yeah, you've seen that, will be called correlation or Pearson coefficient of correlation. You may have heard that. Let's look at that on an example. So here we have this graph we've seen earlier, this scatterplot, where we have on the x-axis the temperature, the outside temperature in Celsius. Each dot is a household, and we have the log of electricity usage for that family. And we want to summarize this by one number. So we know it's possible to use number to summarize things. We've done this in the past. We've used the mean. We used the standard deviation to measure the spread. We've done things like that. Now we need to define correlation, which would be that number, which would tell you if number lie close to a line, basically. So first, it's going to be a number, and be aware of that because in everyday language, correlation is not necessarily a number. People use it to say there is a relationship. So they say correlation, but they mean relationship, whereas correlation is the number that would measure the strength of this linear relationship, which is different, right? So correlation is going to be a number, and it's going to measure how two quantities are associated, right? So it measures the strength of the linear relationship between our two quantitative variables. That's what we want to do. We want to look at this, say, okay, it's linear, it's pretty strong relationship, so we want a number which tells us that. So you know what the goal is. And as you can see from the name, co means together, and relation, so because you have two of them. So this is going to be defined by a formula, and in order to understand the formula, we need to take one step back and look at something called standardization. Standardization. So let's say you start with a set of data, and let's say marks at a given exam. And let's say that you are the first person on the list, and your mark was 76 out of 100. After standardizing, and I will explain how to do this, you get a standardized mark, please note the dot, and let's say that it's 0.5. What does this 0.5 mean? Well, this indicates your difference from the mean. So in that case, your 0.5 is positive, so your mark is above the mean of the group. And the 0.5 what? 0.5 standard deviation. So your mark is 0.5 standard deviation above the mean. That's what it means. Now, if you had a standardized value of -2, it would mean that this value was 2 standard deviation below the mean in the original data set. And sometimes that makes things more readable. First, if you're above or below the mean, and then we'll learn, like that for the normal distribution, for example, something that's coming next, being 3 standard deviation above or below the mean is something very exceptional. So how do we standardize? Well, if you have a value and you want to standardize, first the mean is subtracted from the value, right? And this is why in the end you get a mean of 0. And then you divide that by the standard deviation. In other words, the same thing with formula. Take your value, subtract the mean, and divide by the standard deviation. Let's do it on an example. So the adult female heights are on average 1.65 meters with a standard deviation of 8.9 centimeters. So really so the average would correspond to the mean here. And if we have here the standard deviation, that would correspond to that number. Now we're looking at a particular value, and in our case, it's the height of a person called Diana. So this really is, so let's say that Diana is the first on the list, so that's x1, and what we want is a standardized value. So we just follow the formula. If you want to standardize, first put a dot to say you're standardizing. Then put your value. So let's say I'm working in centimeters. So 158 centimeters, that's my xi. Now I need to subtract the mean, so minus the mean, which is 165 centimeters. That's my mean. And I divide by the standard deviation, which is 8.9 centimeters. Done here. And I'm going to get minus 0.8. That's my answer, that's the standardized value. So that was for question 1. Question 2, interpret the standardized height that you just got. Would be really good if you could pause the video and in your head you try to have a sentence which explains what that means. This minus 0.08 for the standardized value means that Diana's height is 0.8 standard deviations below the mean. Now we did the calculation in centimeters. Would we have got the same result if we had done it in meters? Because the question doesn't say what unit you should use. I think we should try. So let's do it in meters. I want to standardize, and this time I'm doing it in meters. So I want to standardize means I write this dot. So to standardize, take the value you're interested in. If I'm working in meters, 1.58. Subtract the mean, 1.65 meters. And now I need to divide by the standard deviation in meters. So that's going to be 0.089. And remember what we did earlier, and maybe I put a tilde because we don't know yet it's the same thing. And we have to think whether these two things will be the same. I don't need a calculator. If you multiply the top of that fraction by 100 and the bottom of that fraction by 100 and distribute, you will get exactly that. So that's another of the great features of the standardized value. No matter what unit you start with, you're going to be getting the same result. So will you get the same result? Yes. And if you want the same thing in a nicely written form, here it is. And here it tells you a good thing. So the standardized value do not depend on the unit you use. Whoa. And the goal is to tell you how many standard deviations this value is above or below the mean. If you have not lost the plot, you may remember that the goal of defining standardization was really to get a nice definition for the Pearson coefficient of correlation, that number which measures the strength of a linear relationship. So it's going to measure the strength and the direction. Basically, it's going to tell you if it's going up or going down. So you have a set of values, x and y, and x1 correspond to y1 is the same case, and x2 and y2. So what you're going to do is take all these values and standardize them. Then you multiply the standardized value for x and the standardized value for y for the first case. Then you do it for the second case and so on. So you multiply those together and you add and you add. And you divide by n minus 1. And just to give you a feeling of the type of number you could get, when your points are really close to a straight line and it's going up, you could get a correlation of plus 0.93. In that case, it more or less goes down, which is why you get this minus sign, but your points are really much more scattered, which is why you get a value close to 0. Let's try to understand what's happening here. If I look at this first diagram and I take, let's say, this dot, then the x, and let's say it's the fifth dot. Here I get x fifth dot, and I get y fifth dot, and they're both, these two numbers are positive, right? So when I multiply them, I'm going to get something positive, and then I have a lot of dots in this quadrant where both x dot and y dot are going to be negative. So when I multiply them, a negative times a negative is a positive. So what you can see is all these dots here will have a positive contribution to the sum, and all of those will also correspond to positive terms in the sum. So when you add all of those, you're going to get something almost as positive as possible. Very soon we'll see that r cannot go above 1, and this is why you get this big positive number. Whereas in that case, if I take this dot, for example, my x dot is going to be positive, this y dot is going to be positive also. So when I multiply them, it gives me something positive in the sum. But if I take one which is here, for example, here my x dot is positive, but my y dot is negative. So the contribution to the sum is something negative. So now I'm getting something negative. So when I add them, I will get some compensation, and I'm more likely to get something close to 0, which is what is happening there. And so what you see here, these two lines, which correspond to x dot is 0 and y dot is 0, really tell you that's where the mean is. So if you get a dot like this one, which is exactly on this line, so for this one, we're getting that x dot is equal to 0. So the x value is exactly equal to the mean for x. You will never use the formula above to calculate the correlation by hand. What you will need to be able to do is to interpret it. But having seen the picture in the previous slide helps you understand. So first, one thing you need to know is that the correlation R is always between -1 and 1 included. If R is close to +1, it means you have a strong positive linear relationship. In practice, that means you're going to have your dots pretty close to a line, and this line will be going up. Now, if you have a correlation which is close to -1, it will mean your point will be relatively close to a line, and this line will be going down, right? Something like that. Now, if R is close to 0, it means the relationship is, the linear relationship is weak or non-existent. What you can see is R only tells you about linear relationship. If you're interested in non-linear relationship, well, bad luck, you used the wrong tool. It doesn't tell you anything. So if you see something on the scatterplot that's not linear, you can put the correlation in the bin right away. You need something else. So for this to work, as we said in the previous formula, we had this x1 dot and y1 dot, which we were multiplying together. This only works if x1 and y1 correspond to the same case, the same individual. And as we said earlier, if there is a strong association, for example, your points seem to be following something. So you say there is something going on. But if you use R to say, is there a pattern? And clearly in that case there is. You're going to get an R close to 0, which could either correspond to there is no linear relationship, or in a case like that, okay, maybe there is this relationship, but R, which only detects linear one, will not detect that type of relationship. So it's possible to rewrite the formula for the correlation, the formula we've seen before, in expanded form, and maybe that's going to help you understand it a bit better. So maybe you remember there was something here which was called x1 dot, and the way it was built, it was taking, the value x1, the first value, and then it would subtract the mean and divide by the standard deviation. And then this one was y1 dot, which was obtained the same way. Take the value here, subtract the mean, and divide by the standard deviation. And here you have x2 dot, y2 dot, and so on. And you add all these terms, which were built the same way. So here you try to summarize all of this by saying, well, all my terms log, so this is going to be, they all look like x1 minus and so on, and then x2, x3. So here it says it's a sum when I goes from 1 to n. So first time I equal to 1, then I equal to 2, and so on. So that's your xi dot, yi dot to have this sum. And then you multiply by 1 divided by the number of cases minus 1. And here you have a little bit of explanation, just to get you a little bit more familiar with the way of writing things in math. Let's start. You need to guess the Pearson coefficient of correlation by just looking at the scatter plot. So you need to look at whether it's going up or down. And you'll need to think whether it's close to a line or not that close to a line. And that's the part that's hard to evaluate. Maybe I'm not going to click at all. So the answer to this one was 0.9. A lot of students think, it's not that close to a line and would choose 0.6. So the reason why I put in this example is to show you that that is good enough to deserve a 0.9. Next one. Of course, I'm first because I'm the only player. So I'm maybe not going to let it go until the end. So please, on your piece of paper, you could either write one of those numbers or you could write red, green, blue, yellow, but it's important that you actually do it. So this time it was 0.6. So first we see we can eliminate all the values which are negative because those would indicate a decreasing relationship. And this one is clearly increasing. And although it may not seem that good to you, that's good enough to deserve a 0.6 in case you were tempted by 0.3. So the idea is now that in your head, you're going to store the information. A Pearson coefficient of correlation of 0.6 looks like that. Next one. Write something down. So this time, you can see that it's linear. It's still linear, and it's decreasing. So it only makes sense to pick the negative values. Now you need to choose between minus 0.6 and minus 0.3. And if you remember the previous one, it's more or less the same type of spread. So it makes sense that it's also going to be a 0.6, but negative because this time it's going down. Hope you're writing as you do it. Next one. This is getting harder because they're all negative, so you can't, bluntly get rid of some solutions. So really now the goal is to get a stronger idea of what the number could be. And it's minus 0.7. How could you have seen that? It's a little bit better in the sense closer to a line than the one with minus 0.6 that we got earlier. So use as reference point the ones we've already seen. Next one. Again, you can use all the previous one as a point of comparison. I'm going to stop around 10, so please write something down or pause the video. Well, so it's none of the above. So first, what you can see is it's going up. So there was this minus 0.9. That's impossible. Another one which is impossible was this 1.2. The Pearson coefficient of correlation is a number between minus 1 and 1. It's just impossible to get a number above 1. And the last one was 0.6. This is way too good, way too close to a straight line to be 0.6. So it can't be any of those. So it's none of the above. Last one. So close to 1, close to 0, close to minus 1, or close to 0.5. So close to 0, there is clearly a nonlinear. So there is clearly a relationship. I mean, you can summarize this by the type of parabola maybe, but it's not linear. And all R does is to spot the linear relationship, because this one is not linear at all. It's not going to be close to minus 1 or 1, which would indicate either a strong positive relationship or a strong negative one. So here we get something close to 0. So I hope you liked that, and if you did, you can either replay this Kahoot in a single player mode, or what you could do is go back to the slide where it was giving you the guess the correlation game, which is a little bit along the same line. So that should help you, for example, in the assignment, if you get some scatter plot and then you enter and you get 0.4 and you look at yours and say, no, it's much more than that. Get an intuition of what it should be. So I gave you the formula to calculate the correlation by hand. The main reason was for you to understand how it worked and how it was designed, especially by looking at the points in the different quadrants. Then we tried to get an intuitive idea of what these numbers were by playing the Kahoot. And now I'm going to show you how really you're going to be calculating the correlation in real life. You won't do it by hand. You will be using R. So let's say we want to use the electricity usage file again. And we want to calculate the correlation between the logarithm of usage of electricity and the temperature. So what we could do, so if we want the scatter plot, and why not have the scatter plot? Because it's going to, now that we have some intuition, we can check. And the command we're going to be using is this core, which stands for correlation between X and Y. So whenever you want to calculate the correlation, you just use core. So of course, in that thing, the first X value corresponds to the first Y value because they correspond to the same case. So this is what happened on an example. So we have this text file, which is called electricity usage. It's in the data folder. So we ask R to go read it and to create an R object called my data with that. Then we decide to plot it. So we say plot. On the Y-axis, we want the logarithm of the usage. So logarithm against what's on the X-axis, which is going to be the temperature. So in my data, we're going to be extracting using this $sign, the temperature column. Once we have that, what we're going to do is to calculate the correlation of these two variables. Alternatively, what you could have done is to put this into a variable called Y and this into a variable called X. We've done that earlier. And in that case, here you could have put Y and here you could have put X. Once you do this, you get both the scatter plot using plot and you get the value of the correlation. And if you have in mind what we just did, we expect something negative because it's going down according to a straight line. And it's in fact fairly close to that straight line. So this value, which is close to -1, seems in order. So let's see what happened to correlation when there is a nonlinear relationship. And let's look at this example. So what we have here, this scatter plot, gives the average number of points per game for each player. So each dot is a player, depending on their age. Not a good news for me, because it looks like after 27 years old, the performance seems to be going down. And what you can see here is you get a value of R really close to 0. But really, there is a relationship. You could describe it. I could draw this curve that summarizes what goes on. So that this R close to 0 doesn't say there is no relationship. It just says there is no linear relationship, right? So there is a strong relationship, but it's not linear. It's not a contradiction. And now, so that's another example along the same line. You can get R exactly equal to 0 because of the compensation. That's why you needed to see the formula. See this dot, for example, as an X value of 3.5 and some Y value. So the corresponding X1 dot, Y1 dot will be, so for that point, will be the same as this one, except so it will be the same Y value. But the X values are opposite. This one is the negative of the other one, so they will cancel in the sum. Same thing for those two dots. And this is how you can get a correlation, a linear correlation equal to 0, although this is the strongest possible relationship because it's exactly on a curve. So that was the first warning. The next warning is that you don't really expect that one number is going to summarize everything happening in a scatter plot, do you? Even if you use several numbers. So that's why we spend so much time exploring graph. And in case you're not totally convinced, I'm going to show you an example of data sets where really you have the same mean for X, the same mean for Y, the same standard deviation for X, same standard deviation for Y, and same correlation. So basically, all the numerical summaries are the same, but the scatter plot look totally different. So think of this as a warning against looking at the numbers only and not looking at the scatter plot. Look at that. You have several scatter plots, and they're going on the screen one after another. If you look so on the left part of the screen, you can see that they look very different. You can even get a dinosaur. And on the right part of the screen, you can see the calculation for the mean for X, the mean for Y, standard deviation for X, standard deviation for Y, and correlation. These numbers are almost exactly the same for all these scatter plots. And you can see that the common part in these numbers, the common digits, have been written in black. But look at the gray ones. So there are small variations, but extremely small. So after that, you should be totally convinced that just looking at the numbers is not enough. You can have very different looking scatter plots with the same numerical summaries. The next thing we want to warn you about is the fact that correlation is sensitive to outliers. Let's look at this example. So we have a scatter plot of endotoxin, which measures the poisonous content of dust. That's what we have on the x-axis. And then we have PIL-13, the measures of basically your body's reaction, your immune reaction, so immunologic activity. And so the question is, when there is more like basically poison in the dust, does it create more reaction in your body? And so each dot corresponds to an individual. If you calculate the correlation, it's not that close to 0, although this really looks like a blurb with no specific pattern. And the reason for this value, which is not ridiculously small, is that dot. So basically, the apparent correlation is mostly driven by this single point. So if you didn't have the scatter plot, you would say, well, there seems to be a weak linear relationship. Whereas when you look at the scatter plot, you say, who entered this dot? Can I know where this point comes from? What were the values? Let's look at this in a more general setting and more extreme cases. So now we're using like simulated data. So we're going to use these values and we're going to change the values of some outliers. So here we have this outlier, this dot in red, and we decided to give it the value 1, 1. The other value will be unchanged. And we get a correlation, so that's what we enter in R. That's what the answer R gives us. There is only one number in the answer, that's this one. And we get a value close to 0. Step 1. Step 2, we change this remove this red dot, and now it's here. These dots themselves have not changed. What has changed is just that we pull this red dot more to the outside. And look what happened to the correlation. Now it's close to 0.5, so not that small. What do you think is going to expect if we pull the outlier even more to the top and the right? So now we've put 100 and 100 as the coordinates. So this set of points has not changed, but we have this outlier, and look at this. You get a correlation close to 1. So if you don't look at the picture, you say, wow, really, it looks like it's a very good idea to try to predict my y value by my x value. And no, basically the correlation is driven by just one number. So be careful with that. If there are some outliers, they can distort completely the whole picture. Conclusion. Beware of outlier when using correlation, and for that, get the scatter plot and look at it. And that's why you always need to plot your data. So what did we learn and what did you learn? We learned what a scatter plot is. We learned to describe the relationship for two quantitative variables, existence, we call strong, linear, non-linear, increasing, decreasing. We learned what correlation is. This is why we really looked at the formula to try to understand. And we learned about the limitations of correlation, basically the warnings I just issued. Then when you go through this, make sure you know the keyword like scatterplot, positive association, negative correlation. When you hear those words, immediately some meaning should come to your mind. Thank you for listening.